Okay.
Okay? Right. So let's wrap up, and then of course we have to finish the business of the Feynman diagram. And before doing so, I'd like to introduce this idea for natural unit. So whenever we've been doing calculations, we are stuck with a bunch of H bars, C's, and epsilon naught, mu naught, and it's cumbersome. And because these are fundamental constants of nature, in some sense, that's all one. And what I mean by this is that, for example, thinking about the relativity, we have space and time. And to treat them on equal footing, what we did is to multiply speed of light on t, and then we put them together into a 4 vector. So the role speed of light is playing in this is just the conversion constant. From second to centimeters, if you like. So it's sort of similar thing as when you do the conversion from pounds to kilogram or feet to kilometers. You have some conversion constant because you have two different units. And we just grew up in a world where time and space play such different roles that we assign different units for them, meters for distance and seconds for time. But now that we know everything has to be Lorentz invariant, they should be treated on equal footing. So we can actually measure time in the units of meters, if you like. So if we have a clock, and this is 0, and if you pass 1 second, you say, okay, this is 300 megameters. 2 seconds, 600 megameters. Not a very convenient unit, but you can do that, right? So this is the idea of a natural unit. Instead of putting constant C all over the place in our algebra, you just come with some bound to make more mistakes. If you just decide to use the same unit for time and space, you can safely set C to be 1. There's no problem with it. And whenever you have to convert that to SI unit, for example, then you just look at the dimension of the quantity you're calculating. And it's very easy to figure out how many times you have to multiply the C to get to the unit you like to see. And same with H bar. This is again X and P have this uncertainty principle given by H bar over 2. Whenever you see a plane wave, we have P dot X over H bar, and also the time dependence is dt over H bar. Once again, what you're seeing is that you can measure energy in the unit of inverse time, if you like. Or you can measure time in the unit of inverse energy, if you like. So once again, you can set H bar equal 1 without any problems. And the reason why you can do so is that you know the SI unit used to be called MKSA unit, which corresponds to meter for distance, kilogram for weight, second for a time, and ampere for electrical current. So you need to provide 4 different units to describe everything we like to measure. By using these fundamental constants, at least you can set 3 constants to 1 so that you can describe all the other 3 using the same unit. And in nature, definitely there are 3 such constants: H bar, C, and Newton's constant. So you can go to a unit where you set all of them to be 1, then everything can be measured by dimensionless quantity. I'm not saying that's practical, because if you actually use the Newton's constant to be 1, then what happens is that 10 to the 18 gigaelectron volt is 1. Then you're talking about typical energy of atomic excitation to be 10 to the minus 27 in dimensionless unit. So that's not very convenient. But in principle, nature allows us to do so. And if you talk to string theory, they live in the world that the Gn is actually 1. So you can actually do so, and that's a nice mistake. So from this point on, it's just being tedious. I don't set Newton's constant to 1 because that's so removed from what we are doing in a class, but at least I set H bar and C to be 1. And whenever you actually need some real units, pretty much the only thing you need to remember is this quantity. And this is the convenient unit when you do microscopic physics, like in atoms, nuclei, elementary particles. You measure energy using electron volt. And mega electron volt is typically a convenient unit. Fn is femtometer, 10 to the minus 13 centimeters to 10 to the minus 15 meters. And using these units, then h bar times c is sort of order one-ish number, 1/97. And this is the only number pretty much I need to remember whenever I actually work out the measurable quantities. So that's what we are going to do. So that's one thing about natural units. So what we like to do then is that we decided to develop these Feynman diagrams based on the theory we built over the one semester, which has very simple Lagrange. So this piece is for the free photon. This piece is for the Dirac field. Then we have interaction between photon and electron. And this piece was dictated by the gauge invariance. We just had to promote this derivative of the Dirac theory to covariant derivative to make it gauge invariant. And out came this term without no ambiguity. And this is it, right? And we used to write mu naught here, but that's now 1. We used to have h bar c and c squared there. That's also 1. So that really simplifies the expression. And this is it. And in fact, most quantum field theories look like this. And what I have on my t-shirt is the most general quantum field theory you can ever write. You see minus f mu nu, that's over there. You see Dirac Hamiltonian over here, psi d slash psi. D slash the shorthand notation of gamma mu multiplied with any vector. And this is notation by Feynman. You put slash on it, and that's the notation used here. This is the Klein-Gordon field with a covariant derivative. This is 5 to the 4th interaction you have seen with the BEC. The only thing you have not seen is this line called Yukawa interaction, but that's it. You have seen everything. And that's the most general quantum field that you can ever write. So you have actually learned already a lot. And now we are trying to develop perturbation theory with these terms. And psi has annihilation operator for the particle, creation operator for the antiparticle. A mu as annihilation and creation operator for the photon. Psi bar is the complex conjugate of this, that's the creation operator for particle and annihilation operator for the antiparticle. And because each field has these 2 pieces in it, there are 8 possibilities inside this, and we have thrown all of them. So what we like to do is develop general rule how you can put them together to compute a general quantum mechanical amplitude. And we have also talked about this interaction picture. Here I'm not saying anything new. Time evolution operator in interaction picture was given by this expression. You have this interaction Hamiltonian in the exponent, and then you have this time order product. You just keep expanding this exponential in Taylor series, and that's a perturbative expansion, and you insert complete set of states, and that's how we develop perturbation theory. So using this idea, we can start looking at some simple examples of the quantum processes. So let's talk about scattering between this electron and proton. And for that purpose, not only we have the field for the electron, proton is also spin 1/2, so we introduce another Dirac field for the proton, and the mass is different, big M, and I also have interaction of the proton field to Maxwell field, and charge is the opposite from electron, so I flip the sign here. And what you have to do is just this. Following the same rule, every spin 1/2 particle is Dirac field. You know Dirac-Lagrangian, you promote derivative to covariant derivative, and out comes the interaction with the electromagnetism, and that's it. So in the end, all you need to use are these two terms. So you have electron with momentum little pi, photon with momentum big pi in the initial state, with some combination of velocities. Then, using this interaction picture, you bring in these terms out of the Hamiltonian. So, this is for the electron. This is proton. This is a time model product. And then I have electron in the final state and the proton in the final state capital F momentum. And that's the matrix element you need to compute, right? It just follows from the rule we have studied in time-dependent perturbation theory. And then what it's supposed to do is pretty obvious. You have electron in an initial state. You have to first annihilate it. And inside psi E, you have annihilation operator for the electron. So you annihilate that. And when you use this operator, you're looking at the mode expansion of psi E. So this annihilation operator comes together with solution to the Dirac equation, e to the minus IP dot x. And I don't write h bar anymore. Then this psi E bar has this creation operator, creation operator for the particle in it, so that this psi E bar creates electron so that you have electron in the final state. So incoming electron is now annihilated, recreated to go to the final state. And whenever you have C dagger inside this psi bar in mode expansion, you have U bar for the specified final state momentum Pf, e to the I Pf of x. And in between, you have this gamma mu. So all of this end up being this combination of the solutions you have already worked out with the last homework problem. So you just stick in the solution you already know into this expression, and you have to do this algebra or 4x4 matrices. That's the tedious part, but conceptually there's nothing difficult about it. It's just straightforward. This side for the proton is the same thing. This psi p would annihilate the proton in the initial state. Then that is accompanied by, once again, solution of the Dirac equation, U of pi for the proton. This psi p bar creates a proton in a final state, and that comes together with, again, solution of the Dirac equation for the momentum capital Pf for the proton, and in between is gamma u. So that's the piece over here. The last bit we have to think about is A mu. Clearly, there's no photon in the initial state. So all you can do is to create a photon here. Then you have to annihilate a photon because then there's no photon in the final state. And this is time order product, so you can proceed in two different orderings. So if I follow this way of writing it, like in Arabic from right to left, then time flow this way now. You have electron coming in, proton coming in, so you associate the solution to the Dirac equation over here. And you have two different time orderings. One of them is that this operator is earlier, so you create a photon from the electron line, and that photon is annihilated by this AU. That comes to the point of the proton operator. So in this case, electron emits a photon, and the photon gets absorbed by the proton, so that this goes into the final state. And whenever you see this interaction of fermion to photon, you always have this combination of minus IE gamma mu. And on the proton side, we use the symbol nu instead to avoid the clash of notation. And sign is opposite. This is minus, this is plus, because of the opposite electrical charges. Then the only thing that remains to be computed is the photon propagating from here to there. And inside this time ordering, you have the opposite ordering too. So in this case, this operator is earlier. So proton creates a photon, namely emission from the proton side. And then photon is annihilated by this operator later. So the electron absorbs the photon. So inside this expression for the amplitude, you have these two different processes, and you need to add them up in the time order product. But the point here is that you always do this addition of two different time orderings, so it's convenient if you actually compute this sum once and for all, namely that you compute the photon created and annihilated from one point to another for these two time orderings together into a single expression. Then without writing these two terms, in the end we write only one term, where you draw this photon line sort of horizontal. So if I actually look at it this way, this is horizontal, going from the same simultaneous time. Of course, that's not allowed in relativity. Everything has to not go beyond speed of light. But it's just convenient notation of adding two things in one diagram. And this one is called the propagator. And I don't do this on a blackboard because it's just a little tedious, and you have to do contour integral and stuff like this. But when you sum this one and that one as a sum over intermediate states, which of course violate energy conservation temporarily, but if you add them up, what comes in between is a piece called the propagator, which has a very simple expression like this. And this Q in the denominator is the full momentum carried by this photon, virtual photon, where electron goes from initial momentum pi to final momentum pf. So at this point, photon is emitted with a full momentum given by pi minus pf. And that momentum gets absorbed by the proton. So this momentum is the same thing as proton full momentum between initial and final state. And then you put in this full momentum as q mu in the denominator of this propagator, and that's it. So at the end of the day, we find the following. So after going through this time-dependent perturbation theory, all you need to do is write this diagram for the electron and the proton with the following momentum. And in between is this photon emitted and absorbed. And for the initial state electron, you have to annihilate it. So in the mode expansion, you actually bring in this the solution to the Kinematics equation. And then for the final state, this actually comes with a bar on top of it, because this is a more expansive psi bar field up there. The same thing here for the proton. And between these solutions, you put in what is called the vortices. I.e. gamma nu. This is the 4-dimensional spinner. This is 4-dimensional row spinner. In between, you sandwich 4x4 matrix, so it makes sense. And I have index mu here, index mu there. That corresponds to the Lorentz index of the photon field. And try to glue these two lines. I told you you're supposed to put in this propagator, which corresponds to sum over intermediate states in second order perturbation theory we did for when we looked at the scattering of light of the atom. And it turns out that this is it. So in the end, what is called the Feynman amplitude, curly M, is something you can write down immediately once you draw a diagram like this one. So looking at the upper line for the electron, you have mu bar here minus IE gamma nu, u I. And for the proton line, you have mu bar capital PF plus IE. Yes? And connect these two Lorentz indices by using this photon propagator. And this is it. This is the quantum mechanical amplitude in QED. Yes?
Sorry, you may have just explained this, but does the angle that the proton and the electron are making, and then the kind of the bounds mean anything? Because I think yesterday you drew some where they were kind of just going straight across.
Right, so what's going on here is the electron comes in, proton comes in, then they scatter.
Okay.
By the exchange of the photons in between. So this knows the information about which direction the electron is going. This contains information about where the electron came from. If you put them together, that tells you how much electron got scattered by how much angle.
Okay.
And these guys know, again, initial state proton and final state proton. Putting them together, this second line knows how much proton gets scattered. And that comes with this full momentum of the photon. And this Q mu is the difference between initial and final state momentum. So that knows about how much the electron have been hit. It goes into up direction now. So all the kinematic information is contained inside. Okay? Any other questions? Yes?
Can you re-explain the reasoning behind putting the sign on the vertex vectors?
I couldn't hear you.
Could you re-explain the reasoning behind putting the sign on the vertex vectors?
Sure. So it's just that electron has a negative charge, proton has a positive charge. So E is the constant, so I need to associate with different signs in front to indicate that they have opposite charges. Okay? Any other questions? Yes?
Sorry, maybe this is obvious, but the form momentum, the first, like Q0 is the energy of the photon.
Q0
The
is
first
energy
entry
of
of
the
the form
photon.
momentum.
Right. So let's actually look at this.
So yeah, it almost looks to me like energy is conserved in the like not vortex, but you said that's not the case.
Yeah, that's an excellent question, and let me try to respond to that. So looking at the kinematics of the scattering process, let's say electron comes in along the z direction, and this is the velocity of the electron over c, and this is pi u. And initial proton momentum is also along the z direction. So electron comes in, proton comes in, and this is the z-axis. And what can happen to the final state is that they now go off in an off direction, but preserve the energy momentum. The only thing it can do is to maintain the same energy, same velocity, but now it's going in a different direction. This is for the proton. And if you look at this Q mu here, I'm taking difference between initial and final state electron flow momenta. So what you see here is that time component cancels in the difference. So Q mu is this one minus that one. So here I get 0. And that is what I'm going to get. Now, if you look at this, this is the photon flow momentum, which has 0 energy, but has a finite momentum. And such a thing cannot exist. And that's why we kept talking about as an intermediate state in perturbation theory violating energy momentum. If photon has a momentum, it should have energy, but it doesn't. It doesn't conserve energy because of that. So that's a sign that we are looking at this virtual particle, namely that intermediate state in perturbation theory, where you temporarily violate energy momentum conservation, but as long as you pay back, by the time when you get to the final state, that's okay. So that's what I meant, that this photon does not conserve energy momentum. So even though at each vertex, you make sure that incoming flow momentum, find that outgoing flow momentum match up with the exchange photon flow momentum, this photon momentum is what violates energy conservation. Does that answer your question?
Yes, yes, thank you.
Okay. Any other questions about this?
So I have a question.
Yes.
Lee, you talk about the wave function of
Uh-huh.
the outgoing and ingoing
Uh-huh.
particles. This is not that obvious that they can be, the state can be read in terms of this kind of operators acting on the vacuum.
Well, it's not acting on vacuum, right? You have electron in initial state. So this state is the vacuum state with creation operator for the electron and creation operator for the proton already acted on it. And then this psi will annihilate the electron that was already created in the initial state, and then create again to the momentum state, which is in the final state. So this actually looks like PFE, PP. So if you actually do this algebra, you have done with many times, then annihilation operator here, creation operator here, can be turned into anti-commutator, because the other piece is the annihilation operator acting directly on the vacuum state, so doesn't contribute. When you have this anti-commutation relation between C and C dagger, that gives you delta function, and that's how you isolate this particular annihilation operator out of the mode expansion, which involves the integral. So that integral is now gone because of the delta function. And once that's isolated, that comes together with this U solution to the Dirac equation. So that's how this combination comes out. So I'm skipping some of those steps. I'm just highlighting what is the most important aspect of it. But if you just sit down and write down everything in terms of creation annihilation operator with the mode expansion, then you can easily check that that is exactly the quantum amplitude that comes out from this matrix element. Any other questions about this? At least I hope it makes sense. Yes?
Kind of this is a more general question about this method, but I remember when the results people were saying that there were these, you know, we can solve for this by saying that there are these other particles that exist. And so is that when we're doing the contouring of what we're
So you're talking about mu on G minus 2?
Yeah.
And so there is this disagreement of the measured value of mu on the G factor from theoretical projection, and it's still controversial. But the idea is that maybe there's some correction due to particles that had not been discovered yet. And I was going to mention this towards on the very end of the class, but there's something called loop diagram. And this kind of correction would correct the G factor of U1 at order alpha. And these things are part of the standard model. You can compute them. They are powerful people who compute a diagram which is as complicated as something like this, which is incredible. And there are thousands of diagrams like this, and they actually added up. And so they are amazing people who can do that kind of thing. And this has been computed all the way up to this order, and these coefficients have been computed. But this doesn't match up with experimental data, not quite exactly, at the last 10th digit of calculation. And there's a speculation that there may be something else which corrects this. And one candidate, for example, is a muon, actually temporarily turns into its superpartner called scalar muon by exchanging superpartner of the photon called Photon. These particles have not been discovered yet, so they are purely hypothetical. The fact that they are not discovered yet presumably means they are pretty heavy, but because you are allowed to borrow energy as a quantum intermediate state, even heavy particles, which means the energy is high, E equal mc squared, you have to borrow a lot of energy to produce these extra states we haven't observed yet. But as long as you return the energy very quickly within delta t given by h bar over delta E, that's okay. So quantum mechanics allows us to probe even yet undiscovered particles if you look at the very details of the precision experiments. And that's why there has been speculation. Maybe the observed discrepancy of the muon magnetic moment from theoretical projections is due to these unobserved particles contributing to this kind of Feynman diagram. Is that what you're getting at?
Yeah, that's what I was asking. Like,
Okay.
Is that how Feynman diagrams, how we talk about that?
Right. So that was a little bit sidetracked, but anyway. Any other questions about this? Yes.
So I'm a little confused where the electromagnetic field comes. Is it just the field of the proton and neutron, or is there like a background field?
I'm
Are
sorry?
they getting scattered in an ambient magnetic field, or is it?
Well, this is actually scattered. There's no ambient electrical magnetic field. Electron and proton scattered against each other.
And we still get the same field terms that are catching?
No, they are described as different fields. One field for the electron, one field for the proton. But both of them interact with the same electromagnetic field, AB.
They interact with each other's field, or?
Yeah, interact with each other by exchanging a photon. And so that's a good question. This is another thing I want to get up next. So here, I have not introduced any Coulomb potential. But it turns out, if you actually go ahead and compute this, what comes out of this calculation is a Rutherford scattering. Electron has charge, proton has charge. They interact by the Coulomb potential between them. Then in the language of the quantum field theory, the Coulomb interaction is represented by the exchange of the virtual photon. So that's the new concept. When you're thinking of a Coulomb potential, there's a proton sitting in the middle, you're sending electron, and the electron feels the Coulomb potential that had been created by the proton. That's sort of a classical image of what's going on, right? That's how interaction happens. But when you use the language of quantum field theory, potential is exchange of virtual particle. Forces are consequence of exchanging particles in between. Coulomb interaction is the exchange of virtual photon. And as I said, it can come in two different time orderings. Whether an electron creates a virtual photon and proton feels it, or proton creates a virtual photon and electron feels it. You have to look at both of them. But nonetheless, it turns out that what Coulomb potential actually is, once you use the language of quantum field theory, is the exchange of the virtual photon. So that, I hope, addresses your question, at least the beginning of addressing the question. And what I can do is go ahead and really compute that matrix element and show that it indeed reduces to the familiar formula of the Rutherford scattering. Once again, I emphasize, there is no room for Coulomb potential in this Lagrangian. But you have electromagnetic field nonetheless. And in quantum field theory, once you go to quantization, wave turns into particle, namely photon. And photon is a real particle we can observe. We talked about emission of photon from 2p state of atom decaying to 1s state. So photon is a real particle. But once you develop perturbation theory, every particle can appear as the quantum intermediate state, which doesn't conserve energy momentum properly, so it's a virtual particle. But it turns out that virtual particle is what force is about. So that's the new concept that comes out in quantum field theory. So whenever you talk about electromagnetic interaction, you are exchanging virtual photon. When you look at the, hit the knob of a door, and when you hit the electrostatic reaction, then you exchange a photon. When you have atom, an electron circling around the photon, it's constantly exchanging a virtual photon. That is a new picture in quantum field theory. There's nothing like a instantaneous the forces, like, because everything has to can't go beyond speed of light. You have to set information that here's a charge only below speed of light. That means you are exchanging something, and that exchanging something is due to the exchange of virtual particles. That's how information is transmitted, that there is a charge, that's why I have to get scattered by it. And that's because this charge sitting there is sending me virtual photons, and I accept those virtual photons, and as a result, I get hit by it. And that's how I end up going off direction, getting scattered by that. Yes, Kate?
Then does it mean that we can calculate the momentum for a propagator?
Uh-huh.
Meaning that we can actually know the frequency of the virtual photon?
Yes, the frequency is zero, but you see the wavelength of it, right? And so, because this part actually depends on the sine theta, if you put that into Q squared, and if you work it out, this ends up being something like sine squared theta. And in the end, you square this, so probability goes like whatever sine the fourth theta. And that's exactly how Rutherford scattering comes about. So the angular dependence of the Rutherford scattering only has to do with this propagator, whose full momentum is dictated by the initial state and final state. So that is how things work. So let's get to it. So in the end, all we have to compute is this thing here, right? And as you have done in the last homework problem, solution to the Dirac equation looked like this. But in order to understand Rutherford scattering, we take the non-relativistic limit when speed of both electron and proton is slow. What that means is that energy is pretty much dominated by the rest energy of mc squared. you can ignore this. E is m, so this is actually square root 2m. And chi plus minus is a two-component thing that tells you the orientation of spin. And once you have made this approximation, the only piece that contributes is the time component. So u bar gamma mu u, if you go back to the original Dirac notation, this is u dagger beta. Gamma 0 is beta, so that's a unit matrix. When you look at the spatial direction, that's the alpha matrix. So time component is 1, spatial component is alpha. And alpha matrix, if you remember, is off diagonal with the Pauli matrices. Now we decided that lower two components can be ditched. You have only upper two components. Even if you add alpha on it, then this goes down to lower components. But this guy has only upper components, so that vanishes. So in non-reduced limit, this is actually very simple. This is square root 2e, 2m. This is square root 2m. Only thing there is a time component, which is a unit matrix. And I still have this two-component piece, which knows about the spin orientation, but that's it. The same here. This is only time component, and then I have 2m of the proton mass, 2m. And this only time component, that's a unit matrix. The only thing I need to care about is this two-component part of the wave function that tells you about the spin orientation. So, at the end of the day, this amplitude, this q squared has no time component. So this is strictly spatial component of the momentum transfer. I have minus IE plus IE, that's E squared. Propagator has this minus IE. And in summing over this Lorentz indices mu and nu, only time component contributes. G00, that's 1. And what I have to do is insert this identity matrix. So all there is this two-component piece of the spin wave function for electron and proton. And because this is actually directly initial state wave function and final state wave function, it tells you that if the initial state is spin up, final state is also going to be spin up, then this product is 1, as long as spin doesn't change. Same is proton. So amplitude really reduces down to just 1 over momentum transfer squared. It's actually very simple.
Sorry, what happens to the square root of the masses? Should this also be
Yeah, so that's an excellent question. So there is this masses of 2m, 2m. And this gets taken care of when I actually carefully write down expression for the cross-section. That's what I'm getting to next. So thank you for asking that question, Sam. Any other questions? Yes?
I have a question about the logic that we say electromagnetism, like they exchange force through photons.
Yeah.
I feel like that's because we basically couple a mu, which we expand as photons.
Right.
So I think it's kind of like a circular argument where we say that, oh, we discover that electromagnetism exchange their force as photons.
Oh yeah, so I'm not claiming that we discovered electromagnetism here, right? But we are switching the description from instantaneous Coulomb potential, which conceptually really does violate causality, to the exchange of virtual photon. And in quantum field theory's point of view, that is the right description of what Coulomb force is actually about. So it's a different language from one to another, but the language in QFT is in some sense more precise, more relativistic, and then it's also quantitative. And it turns out that the Coulomb interaction is lowest order perturbation case. There can be even corrections at higher orders, which you cannot do with the classical Coulomb potential, but you can do with the quantum field theory. So it's more correct, detailed, and predictive if you use this language of the virtual photon in the end. Yes?
Can we say that a charged particle are emitting virtual photons ceaselessly all the way in every direction?
That's right. So whenever you have a charged particle, it's emitting virtual photon in all over directions.
Yes, but how do we reconcile the idea that when two charged particles getting farther away from each other, and the interaction of their electromagnetic field is getting weaker, but we don't expect the frequency or wavelengths of an emitted photon to change?
That's a great question too. So if you look at this expression, when your scattering angle is large, sine theta is large, spatial component of photon momentum is large, so you have to violate energy conservation a lot more. And that virtual photon doesn't survive long, namely it doesn't go very far. So big scattering can happen only when electron and proton come pretty close to each other. But when they're far away from each other, you can exchange virtual photon only when virtual photon doesn't violate energy conservation very much, so that it can go over long distance. So for that to happen, then this virtual momentum has to be small enough so that the violation energy conservation is little, which means then scattering angle is small. So the classical idea that particles scatter a lot when they come close to each other is now represented by how much virtual photon can go for a particular process. So that information is in here as well. Thank you for asking that question. Yes?
Kind of on the same thing, does it make sense to think of the virtual photons as like the number of interactions with those virtual photons falls off as like 1 over r squared, like it would for the field?
Yeah, so it does. So when you actually look at this expression of 1 over momentum transfer squared, this is probably better way of looking at it. Momentum transfer to photon is inversely proportional to the distance it can propagate. So when q squared is non-zero, you have borrowed energy. So the virtual photon doesn't survive long. It can only go at the speed of light, not beyond that. So how much it can go is dictated by this ratio, and that's the distance of how far the interaction is acting on. So that is the information in here. So this actually corresponds to really the force falling off at long distances at the end of the day. Thank you for asking. Yes, another question over there.
So does like magnetism and current magnetism pop out of a higher order term here, or is that a different interaction?
The magnetism is actually built in too, so that I will get back to it once we write back the cross section. Okay, so now you have all the elements needed to get this quantum mechanical amplitude. The only thing you need to know beyond that is how to compute this matrix element to the scattering cross section. The only thing we need to be careful about is the way you look at this commutation relation, momentum P and Q. We have decided to use this Lorentz invariant normalization of them. And as you might remember, if you look at the delta of 0 for the spatial momentum, this is actually dqx e to the I p minus qx, right? And you're saying this p and q is the same. So this is actually volume of space. So this actually ends up having 2e particles in unit volume. So that looks like a weird convention, but we wanted to have a full Lorentz invariance of the theory. This was the Lorentz invariant expression, that's why we decided to use it. But because we use this normalization of creation-addition operator, we have to take care of this issue that there are more than one particle in a given volume. So at the end of the day, cross-section has to be divided by this number of particles in a unit volume. And it comes with the flux factor 2, so there comes relative velocity between them. And then you sum over all final states. Here again we're using this Lorentz invariant form of the phase space, which you have seen in a mode expansion of the field operator. So this is actually nothing but what comes out from mode expansion of the operator when you actually go ahead and compute this from the first principle. Then you square this Feynman amplitude squared, because it's probability, and you have to conserve for momentum, and that's it. And this 2e, 2e1, 2e2 in a non-towards limit is nothing but the mass of these particles. And that ends up canceling these 2m and 2m factors. So these factors properly go away. And the rest you can just go ahead and compute it. And there's nothing sort of fundamentally conceptually difficult in here. So you're just plugging numbers, use the correct momentum transfer and so on, and then comes out the answer. Alpha squared, 4p squared, beta squared, sine 4 beta over 2. Beta squared, beta 2. Let me preface a little bit. So right now, I did the non-relativistic approximation throughout, but in the expression I'm writing, I'm allowing for the electron momentum to be finite, but the proton momentum is still static, because proton is a lot heavier, to just see the glimpse of the first correction coming from relativity. And the fact that this actually goes like 1 over sine to the 4th theta over 2 is exactly the same thing what you see in Rutherford scattering. And when you set beta to go into 0, then this piece becomes 1 over b to the 4th, because p squared beta squared. That's also what you might remember from the Rutherford scattering. And so this actually ends up precisely reducing to Rutherford scattering when you do the non-relativistic limit. So what we used to think as the Coulomb potential is really the exchange of the virtual photon. That's the thing we learned from this exercise. But now that I can also keep beta finite, I have some correction here. And this is something we can understand too. So I mentioned this fact that when you take the massless limit of fermion, chirality is conserved, which means if the electron comes in on top of the proton target and gets scattered, and let's say this electron has positive helicity, which is positive chirality in the massless limit, it has to stay that way because it's conserved if electron is massless. Massless electron is going with speed of light, so that's the limit where you can ignore the mass of the electron, so beta is 1. Then what you see here is that 1 minus sine squared theta over 2 goes to 0 when theta is pi. And this is not something you have seen in non-relativistic Rutherford scattering because beta is practically 0. So in addition to reproducing Rutherford scattering, you are seeing something new here. And this new thing actually makes sense because once you consider the fact that the helicity of electron doesn't change before and after the interaction, when an electron comes in with a positive helicity and gets backscattered, at theta equal pi, but retaining the same velocity, initial state angular momentum and final state angular momentum don't match up. It violates angular momentum conservation. Therefore, there shouldn't be probability for it. And indeed, it vanishes. So not only that you reproduce what we thought as the Coulomb scattering, we do reproduce that, but now that theory is fully relativistic, you don't have to stay with a non-relativistic regime. You can go to close to the speed of light, or even the exact speed of light if the particle can be assumed to be massless. And if you do so, you start seeing this new phenomenon like probability vanishing for backscattering. So what you might remember from Rutherford experiment is that you actually shoot alpha particle into the foil of gold, and the fact that it bounces back was the discovery that the charge is concentrated in the middle. But he was lucky, right? If he had said in relativistic electron there, then there's no backscattering because it vanishes. So it was good that he was doing experiment non-relativistically, but in the relativistic limit, you start seeing a new selection rule like this one, and that's how you can even compute processes now that you know this Feynman diagram, even when the particles are particles are relativistic. And if you actually think about this, how the helicity of the electron remains conserved looks magical. If you are thinking about sort of classical picture of the Coulomb potential, and if you have spin orientation, as I said already in non-relativistic limit, spin orientation doesn't change. And that's indeed what we could rederive using the Feynman amplitude. But when you go to relativistic speed, I'm saying that spin is always oriented together with its direction. So what's going on here is that Coulomb potential is an electric field. Electric field in the moving frame of the electron would induce a magnetic field. So this electron not only sees the electric field, but also magnetic field at the same time because of this Lorentz boost factor. And that magnetic field would induce the rotation of the spin in such a way that spin rotates by exactly the same amount as the scattering angle, so the helicity remains the same. So somebody is asking a question about a magnetic field in this process. Indeed, magnetic field does play a role. There's no ambiguity. Everything follows from the first principle. And if you look at this classical picture, it looks too magical that this effective magnetic field induced by the Lorentz transformation would rotate the spin exactly the same amount as how much electron gets scattered. But once you know the chirality conservation for the massless electron, then this becomes obvious. So that's the way you can start to understand even what happens in a relativistic regime of this kind of scattering experiment. Any questions about this? Yes?
Is there an intermediate, like, where maybe it's going like, what happens when it's going like almost relative?
Yeah.
Almost relative.
So in between is when beta is not quite 1,
Okay.
but some intermediate number. When it's 0, that's a non-relativistic limit of Rutherford scattering. And intermediate, then you start seeing that this backscattering starts getting suppressed, but not quite exactly 0 yet.
So it'll just be what squared.
Yeah, so everything is continuously connected.
Yeah.
Okay, any other questions? Yes, Jackie?
Sorry, could you explain how the backscattering leads to violation of velocity conservation?
This one, yeah. So in the case of backscattering, electron becomes wing with a positive velocity, is the proton. Then classically you would think the Coulomb scattering would allow for the backscattering. But in the limit of auto-relativistic electron where you can ignore the mass, the chirality is conserved, So whatever came in as a positive priority should stay with a positive priority. So then spin is now moving this way. So initial spin is pointing this way, final state spin is pointing that way. So you're changing angular momentum.
Oh,
So it's not
angular momentum is
conserved.
fine then. Okay.
That's why it's forbidden. And if you look at the lecture notes, you see the scattering process of electron comes in with right-handed and going out with right-handed. That amplitude is proportional to cosine theta over 2. And this is actually proportional to the energy of the electron. But this one is proportional to the mass of the electron. So when you can ignore the mass of the electron relative to the energy of the electron, you see this is suppressed because it doesn't conserve chirality. So that's what you see here. At the same time, when you look at this dominant contribution to the amplitude, it's proportional to cosine theta of 2, and that's how this vanishes when it's precisely backscattering, because it doesn't violate conserve angular momentum in that case. So once you actually see these amplitudes, you can understand various limits, why it vanishes in certain kinematic regime, which one is dominant, which one is suppressed. So this is something you can understand very intuitively once you get used to this kind of idea. Any other questions here? Yes.
Did you just say that because of we plus the relativistic effect, so that the helicity will align with the particles?
Right.
Sorry for being slow, but could you explain again?
Yeah, so because if you remember this discussion with the Dirac Hamiltonian, it didn't commute with orbital angular momentum, it didn't commute with spin. But it commutes only with the sum of them. But if you look at the direction of the angular momentum along the momentum direction, this of course commutes because Hamiltonian commutes both with J and P. But when you actually dot L on P, L is the x cross P, that's always perpendicular to the momentum. So that piece drops out. So this is actually nothing but spin along the momentum direction. So spin is not conserved. Spin does change because of this, the Lorentz transform magnetic field, it does rotate. But if you look at the spin along the direction of the momentum, that is conserved. That's why talking about the helicity is much more convenient in relativistic theory, because that's still conserved. You can use that as a label to specify your state. Okay? Any other questions? Okay, then let's get to just one more example of the final diagram, which is the final exam problem, so you want to pay attention to that. And again, once you have the solution to the Dirac equation, everything is straightforward, nothing conceptually difficult. But we like to talk about the process of pair annihilation and pair creation of particles, like E plus E minus going to E plus E minus. And once again, you have electron and positron in the final state, initial state, and you use this operator. And inside psi, you have annihilation operator of the particle, so that annihilates electron initial state. Psi bar has annihilation operator of the antiparticle that can annihilate the positron. So electron and positron then disappears from a universe. All there is now virtual photon that doesn't conserve energy momentum. So when electron comes in collider experiment, then that's relativistic. So I'm ignoring the mass, so beta is 1. Positron comes in. In opposite direction. And what is formed here is the virtual photon, whose whole momentum is now sum of the two. And because electron and positron in a collider experiment comes head on from most of the direction, there is no spatial momentum anymore. They precisely cancel, but there is energy. Again, this is the virtual photon, because if the photon has zero momentum, it should have zero energy, but it does have a lot of energy here. So this again violates energy conservation as a quantum intermediate state. But this energy is now capable of creating something. And that's when we introduce mu1 field now. This is the field for mu1, this is the field for the electron. And psi mu has creation operator for the antiparticle, mu plus. Psi bar has creation operator of the particle, namely negative mu1. So it can now create particles that didn't exist at the beginning of experiment. So annihilation and creation can really happen in QFT, and then you can compute this process. Then it's easy to translate this chain of operators into Feynman diagrams. And somebody was asking this question because I was inconsistent on Wednesday. Whenever you actually have particle, you follow its number, which is positive. Electron number is positive for electron, so it's going this direction. But for positron, electron number is -1, so it's carrying -1 forward. And when you draw Feynman diagram, you draw the arrow in opposite direction to indicate that. So this is where you sometimes hear about this idea that antiparticles traveling backwards in time. It's not. It is the antiparticle moving forward in time, but because it carries -1 number, you draw the line opposite. But anyway, that's what you might have heard about somewhere before. And then electron-positron is fully annihilated here, turns into virtual photon with only energy but no momentum. That's the thing in here. And then this operator here creates a, sorry, I draw this backwards. Muon, which is a particle, so carries the charge forward. Anti-muon is the antiparticle, so it has a -1 number, so that's why the arrow is drawn backwards. And this is the Feynman diagram. And once you have the Feynman diagram, again, you know exactly what this amplitude looks like. Following the electron line, this is now described by the negative frequency solution. So V bar, P bar of the four momentum, minus I gamma mu, U, Pi, that's the four momentum of the electron. Then I have this photon propagator in the middle. And then I also associate Dirac solutions so here I'm using Pi momentum, P bar I momentum, Pf momentum, P bar F momentum. The bar means you're talking about the antiparticle. And for this line here, you start out with positive energy solution for electron, then hits this vertex minus I gamma mu, and turns into negative energy solution, V bar, P bar I. So if you follow the arrows, you can immediately write this one down, starting with U, vertex, and V bar. Same idea over here. Again, you follow the arrows. You start out with this one here, because this is where the arrow begins, and that's the negative energy solution for the anti-muon. Then hits the vertex over here, and turns into the solution for the positive energy solution in the end. So if you follow the arrows, you can immediately write this one down. And connecting to these vertices is again the virtual photon, and we know the propagator for it. And this is it. And all you have to do in the final exam problem, which is a bit more tedious than this Coulomb scattering, it turns out, but you just plug in the solutions and do this 4x4 matrix, and you might let Mathematica do the algebra for you. And then there comes out 4 different combinations for velocities, but 2 of them are identically 0 because that violate chirality. Electron is very relativistic here, so you can ignore the mass of the electron. So if electron is right-handed, then positron has to be left-handed. If electron is left-handed, positron have to be right-handed. So there are only 2 combinations of velocities here. And also, if you actually work this out for 4 Lorentz indices, it turns out that only x and y component don't vanish. So you don't need to compute 4 things, you need to compute only 2, even though it's easy to check. And because this new index is summed over with the new index over here again you need to compute only 2 Lorentz indices, x and y, so that saves you some time. And then you plug in this the propagator in between. And in the final exam problem, I'm asking you to keep the mass of this final state particle, because instead of muon, I'm asking you to look into something called even bigger brother of muon called tau lepton. And then you can do the collider experiments, and that actually happens in Beijing electron-positron collider. X. And you have electron, positron coming in. Then you produce this pair of particles called tau minus and tau plus. But it's the same idea as muon, except that you want to keep the mass of the tau finite. And because the mass is finite, then you have 4 helistic combinations: left, left, right, right, left, right, right, left. So 2 combinations for the initial state, 4 combinations for the final states. Then you just multiply them, sum them over, and you get 8 amplitudes out of that. And then what you can compute then is as a function of central mass energy. Cross-section stays 0 and start to rise when energy is 2 m tau c squared. Because below this energy, you don't have enough energy to create these particles. Each particle costs rest energy of m tau c squared. And this is the final state you really observe, so it has to conserve energy momentum. So it starts out 0, and you can compute how this rises. And you can compute what is the size of the cross-section, and we use this unit called nanobarn. And then compare that with experimental data. And I have to warn you, they don't exactly agree, because we are doing lowest order perturbation theory. When you actually do this experiment, you also have to include the fact that initial state electron can emit a hard photon. The effective collision energy is less. So you tend to basically move center mass energy down, which suppresses the cross-section. So they don't quite agree. But at least you see that there's a correct order of magnitude. They agree within a few tens of percents, and then you can predict this rise. And then I put in the reference for the experimental paper. You can directly compare your calculation to the experimental data. So this is now something you can do. And just to give you an idea how this algebra goes, I'd like to just do one example. So just to refresh what the positive energy and negative energy looks like. So for B plus minus, you are supposed to kind minus plus. There was a typo in earlier version of my slides which I corrected, so it's now the correct version. And the lecture note always had the correct sign there, but just warn you, if these two signs are the same, that's a typo. Hopefully you don't have any trace of it anymore. So this is the solution. Any pi plus minus was given by this eigenstates of sigma dot p matrix. And suppose you're doing this final state side of things, U bar EF gamma mu U P bar. Suppose you're computing this. And if you're looking at, for example, this helistic combination, then V minus is and let's say this has a momentum like that. Then chi minus is given by that one. And because physics is actually invariant, I can always choose phi to be 0. That's what I have done here. So you don't need this. U plus and this is actually in opposite direction. Which is obtained by changing theta to pi minus theta, phi to phi plus phi. Then you go to the opposite direction of the momentum. And plus, should use that plus, but when you change theta to pi minus theta, cosine theta over 2 becomes sine theta over 2. Sine theta over 2 becomes cosine theta over 2. But shifting phi by pi, that gives me minus sine. So these are the solutions. And you put that in here, again remembering that this is 1. You can work it out. It turns out that when you put 1 here, then you have E plus M, E minus M, E minus M, E plus M. It turns out that they cancel. So time component is just identically 0. You don't need to compute this. The only thing you need to work out then is the spatial components. And it looks like 2E Q sine theta I minus sine theta. So this combination preserves chirality, so it's a dominant combination. But if you look at the combination like U plus gamma mu V plus, that violates chirality, then it turns out it's suppressed by the mass. So it looks like this. So in the massless limit, this indeed does vanish, just like what we talked about in this relativistic Coulomb scattering. And when you do the same calculation with the initial state, as I said, there's only x and y components. And once you glue them together, you can predict amplitude like this. And Feynman amplitude turns out to be extremely simple. In the way this 1 plus cosine theta comes about, it's just because of the theta dependence of the final state Dirac solutions. And 1 over q squared ends up completely cancelled by the normalization of these solutions. That goes like square root 2e each. So it becomes this dimensionless combination. And this dependence on the angle makes sense. Electron comes in with right-handed velocity. Positron comes in with a left-handed velocity. So there is a net 1 angular momentum in this direction. When the tau goes out with right-handed velocity, anti-tau with a left-handed velocity, then along this direction, there's a net 1 angular momentum. And when cosine theta is -1, which corresponds to backscattering, initial state has total spin this way, but final state would have total spin that way. Again, that will violate angular momentum conservation. So the amplitude vanishes, and that's this combination 1 plus cosine theta, so that should make sense. On the other hand, when you compute the case when this velocity is split, that violates the chirality conservation, so amplitude correspondingly is suppressed by the mass, so it correctly vanishes in a massless limit. Sine theta angular dependence also makes sense, because in this case, along this direction of tau, there is no angular momentum. So if tau is going forward direction, initial state has angular momentum 1, final state has 0, that doesn't conserve angular momentum, and indeed amplitude vanishes. Also, when it goes backwards, initial state has angular momentum 1, final state once again has angular momentum 0 along this axis, so amplitude vanishes because it violates the angular momentum conservation. So this is the way you can sort of see that after algebra, your result actually makes sense. And lecture notes have all the amplitude expression for the massless view of final state. So only difference from the lecture notes is that you have to keep the mass finite, which makes it a little bit more tedious, but once again, it's just the matrix multiplications. They're conceptually nothing difficult, and that's how you can compute it. And at the end of the day, after solving for the delta function for the full Reynolds conservation, it all reduces down to the solid angle integral. It depends only on theta, so you need to keep actually only the polar angle dependence. Theta is the velocity of the final state tau. S is just a notation, which is center of mass energy squared, just a common notation called Mandelstam variable, called after our late colleague Stanley Mandelstam in the department. And so once you compute this m, from that, you put it in, square it, cosine theta integral, and the rest is the phase space factor and the energy denominator, and then comes out the cross section. And the cross section now has dimension of 1 over energy squared. To get the correct unit as the cross section, you put in h bar c squared to convert this into the unit of centimeter squared, and you express that in the unit of nanobarn. Nano obviously is 10 to the minus 9. Barn is a typical cross section people knew in old days for various scattering processes, and 10 to the minus 24 square centimeters. So this is barn, this is nanobarn, and you express this in the unit of nanobarn. That's how you can compare your calculation to the experimental paper that is cited in the final exam problem. So that's it. So any questions about this? And I scheduled office hour next week, not on Friday, that's the exam, but some earlier days so that you can come and ask questions. And then hopefully there's no real conceptual issues in carrying this out. and hopefully lecture notes are useful for that purpose. And the other two problems are something we have done before. This the first problem on the two-dimensional Dirac equation, you basically do the same thing that we have done the previous homework problem of solving Dirac equation, but you can explicitly impose reality condition formula on fermion or projection operator for the white fermion. It's very easy to do so in 2 dimensions, so you can see that in the first part of the homework problem, the finite exam problem. The last one is this idea that the dark matter is really the dominant mass in any galaxy, and I'm asking you to look at one data. And once you know how stars are moving inside this galaxy, you measure the circular velocity. Circular velocity should be given by the total mass of dark matter inside the Newtonian mechanics. But once you know the total mass within a radius, you can also compute the escape velocity. So dark matter is not populated below escape velocity because they escape. And mass times the escape velocity then sets a scale for the Fermi momentum. And below the Fermi momentum, you can put dark matter states in. And if dark matter is a fermion, then below the Fermi momentum, there are only finite number of states you can populate. So that's the maximum number density you can put in. So if the mass is too light, Fermi momentum becomes so low, the mass density doesn't match up to observation. So that way you can actually derive a lower limit on the mass of the dark matter if it happens to be a fermion. So this is related to the first half of the course, talking about this Fermi statistics and the Fermi gas. But it turns out that you can see this quantum mechanical restriction on the number density of dark matter particles in the galaxy on astronomical scale. That's how we know the fermionic dark matter has to weigh above certain mass. So that's the last piece of the problem, and hopefully that is actually fun to look at. So that's the end. Sorry I went over time, but we have come a long way. Let me just wrap up quickly. So quantum physics has this particle wave duality. Everything is particle and wave at the same time. Quantum mechanics starts with a particle to approach this problem. But when you do so, for example, things like the Bose-Einstein condensate is a highly quantum state of matter, which is very difficult to deal with in this language. On the other hand, QFT starts with wave to approach this problem. And we are doing the same thing, but in the case of BEC, it's so quantum from the particle point of view, going back to classical wave in QFT was the good language. And once you go QFT, even though it deals identical physics, that has the quantum statistics built in, you can talk about the systems that doesn't conserve the particle numbers, like BEC and BCS. So that's where QFT was already needed in a non-relativist system. Once you impose relativity on it, then there was no quantum mechanics. You really had to go for QFT language. Then we could now compute processes where you can emit photons, which was sort of the big advertisement at the beginning of quantum mechanics, but now you know how to deal with it. You can compute the emission of photon, you compute the scattering of photon, why the sky is blue, and so on. And then we fully combine QFT together with electromagnetism and relativity, and then we finally arrived at QED. And using this language of the Feynman diagrams, you can literally compute processes like electron positron come in, they disappear from the universe, and out come the new particles that didn't exist at the beginning, like muon and tau. And those processes do happen. You see the experimental data for it, and you can even compare your calculation to the data directly. So that's, I hope, what you learn over this semester. So that's it, and good luck with the final exam.
Thank you.